Hey folks, welcome to my channel Number Pen. So today we're going to look at the topic continuity of a function f of x at x equals a, right? I thought I'll dwell upon this topic in this video because a lot of the problems which you're going to solve going forward depend on understanding continuity of a function and differentiability of a function at a particular point, right? So let's talk about continuity of a function and understand this better using a few examples as we go through this video. So you have this statement right in front of your screen. What does continuous actually mean? The English definition of continuous is without any break or gap, right? So if the graph of a function y is equal to f of x has no break or gap or jump, then it is said to be continuous, right? And a function is not continuous is called a discontinuous function. So, how do we actually determine mathematically if a function is continuous or not? Right? Let's assume that we've been asked to determine if a function is continuous at a particular point x equals a. Now, what does continuity mean? I go back to the English meaning, right? Without any break or gap. Now, when I represent this mathematically, what it all means is let me assume that x is going to take a value a plus h, which is what I've represented here. As a let me use the pen if that helps. Yeah. So here and x taking a value a plus h, where h is infinitesimally small, tending to zero, right? And if as x tends to a plus h, which is what in the world of limits we call it as the right hand limit, it still equals f of x at x equals a, right? Which means that there is no break in the function y is equal to f of x as we pass through a, right? So, and this is applicable both for left hand limit and the right hand limit, right? When I say left hand limit, what I mean is a point which is to the left hand side of the point A, which is where we are determining continuity, right? And when I say right hand limit, it means that a point which is very close to A but on the right hand side of it. So, how do we represent this mathematically? So, x tending to A plus h and x tending to A minus h, right? Where h is tending to zero, which is infinitesimally small. So, so how do we actually determine if a function is continuous? If our limits when x tends to a plus equals x tends to a minus equals f of x at x equals a. So, which means that there is no break in the graph. I hope you're able to kind of mentally visualize this, right? So when I take a point, I'll repeat this again. When I take a point to the left of A, which is very close to A, and when I take a point to the right of A, which is very close to A, still tending to A, which is what we represent as, A minus H and A plus H, and call them limits because H is infinitesimally small, tending to zero. That becomes equals f of x at f is equal to x equals A, which means, it is equal to f of A. So a function is said to be continuous at a point x equals a if it is left continuous as well as right continuous and satisfies the above uh, equation, right? So we need to arrive at the left hand limit. We need to arrive at the right hand limit and make sure that both are equal and at the same time they are equal to f of x equals f of a. Now I'll help you understand this with a few examples along with their graph because it becomes a lot more clearer. And here is another important thing. You will come across cases where there will be a limit existing as x tends to a. It could be an a minus or an a plus, which means it could be a left hand limit or a right hand limit, but is not necessarily equal to f of a, right? Then the function is still discontinuous at f of a. We'll look at a few examples in our subsequent videos. So, let me explain this with an example, right? Let's take a very simple example, and for a minute, don't really pay attention to the graph on your right. And I'm going to use this example y is equal to x square, which is a simple parabola, which means that x takes positive and negative values and y always takes positive values. And that is why you see the graph the way it is on your right. And let's apply this equation here again. Now, for applying this equation, we need to choose a particular point A, right? Now, let me choose a particular point, say 1, right? I want to understand if this graph is continuous at the point 1, right? So let me write this down again here. I'm going to replace this. My A here is 1 and my H is 0, and my f of x at x equals a is nothing but my x square, right? So let me pull out x square, right? So x equals 0. So the way we usually solve these problems is, we evaluate the left hand limit, which is my f of 1 plus h, right? Which is my limit, which is nothing but my 1 plus h, the whole square. That's equals 1 plus h square, 1 plus square plus 2 plus 2h, right? So as h tends to 0, I have 1 plus h square becomes 1 plus 0 plus 2h becomes 0, which is equals 1, right? So this is my left hand limit. Let me go to my right hand limit and I'm going to replace this as 1 minus h, right? Now rewrite this 1 minus h the whole square, that equals 1 plus h square minus 2h, which means 1 plus 0 minus 0, which still equals 1, right? And then I also go back here and write my f of 0, which is my f of 0, right? Nothing but f of 1, I'm sorry. Right? I write f of 1, which is my square, which is 1 square, which is nothing but equals 1, right? So now we have, let me use the draw pen here so that we understand this better. So we have this equation, equation 1, and we have this equation, which is equation 2, which is my right hand limit, and this third equation, which is my left hand limit. all the three are equal to 1, right? Which means, as per the definition of continuity which we just now saw, it means that this function is a continuous function at the point x equals 1, right? I'm going to change this. I'm sorry, guys. X equal to 1, right? So let's take a minute to look at the graph, right? You see that this graph is a continuous function, and it'll be interesting to see how this graph turns out to be at x equals 0, because the curve has got a point of inflection at the point x equals 0, right? So let me do this. So you have understood why the function is continuous at x equals 1, which is like, at some point here. So these are the points 1 comma 1. When I take a value x which is very close to 1 and it's tending to 1, which is what we call as our 1 minus h on the left hand side, and we call it as 1 plus h on the right hand side, right? They also tend to the value at x equals 1, right? Which means my left hand limit is equal to my right hand limit is equal to my value at x equals 1, right? Now, as I said earlier, it'll be interesting to see what it turns out at 0, right? At x equals 0. So we will just replace this by 0, and my f of 0 is 0, right? And my right hand limit of 0 plus h, that's going to be 0 plus h square, which is nothing but my h square, which makes it 0 again. Next, I have my 0 minus h, which is my left hand limit. And then I do 0 minus h the whole square, which is again minus h into minus h becomes plus h. Again, plus h square, which is again 0, right? So here again, we see that, equations 1, 2, and 3 are all equal this time to 0, right? So which means the function, going back to the graph, the function is continuous at x equals 0 as well. So the reason I took this example is for two reasons. One is this is a very simple example, and point number two, it helps you understand, how do we determine a function is continuous at a particular point or not, right? So the function y is equal to x square, to conclude, is a function which is continuous at all points, right? You can pick up any example, you can pick up any point at on the graph and work it out the way we worked it out just now, and see that the left hand limit equals right hand limit equals the value at um, x equals a, right? Now we'll move to a couple of other functions which are quite interesting, along the same lines, and I've kind of put them out here. One is a mod function. So a mod function is defined as this, right? For values greater than or equal to 0, we have f of x equals x, and for values lesser than 0, we have f of x equals minus x, right? Now, from our previous examples and from this example, we know that, uh, you know, the point of inflection is again 0, right? So we will study the continuity of this function at the point x equals 0, and I'm gonna write this again for you guys. What's my f of 0, right? My f of 0 is 0, which is nothing but my x. F of 0 plus h is my right hand limit, so it's nothing but my f of h, which takes the value, which means that f of 0 plus h is a positive number, right? 0 plus h is a positive number. It is a number lying to the right hand side of 0. So, which means I will go with this function, right? I'm going to highlight this, right? And I'll probably use the same color down here for the ease of understanding, right? And I'm going to use the same color out here. F of h equals h, which is 0, right? And I'm going to come to my left hand limit. Again, a function. So let me write this using the limits terminology. And to calculate our LHL, we have x tending to 0 minus h, which means that x takes small negative number, right? So, which is f of minus h, right? Which is again minus x, right? Now, let's change the color for this. Use the green color because we're going to use this function because x is going to take a very small negative value. So we are using this function, what I've highlighted here in green. And it's my minus of minus h, which is my plus h, right? You'll have different textbooks discussing it in different ways. And what I would recommend is uh, when you're working out these problems, stick on to one particular methodology, right? So the methodology I use here, or the way I do it is, I always assume that x tends to a plus h or a minus h, and then h is an infinitesimally small number, but it is a positive number, right? So I have minus of minus h. So let me take a minute to explain why am I doing this here. So f of 0 minus h is 0 minus h is a negative number. So I apply minus of 0 minus h, right? Let me write this way so that it becomes a lot more clearer. And then minus of 0 becomes plus h, and h tending to 0 becomes 0, right? So here again we have all the three equations, right? Which is your this equation f of 0, this equation which is your right hand limit, and this equation which is your left hand limit, all are equal, right? So hence we know that the function mod of x is continuous at x equals 0. And I want you to pay close attention to this graph because you will see that this point x equals 0 is very important to understand when we jump into the topic of differentiability in the subsequent videos, right? So right now we know that the function is continuous at x equals 0, and with that we will move on to our third example where we'll discuss a case where x is not continuous at a particular point, right? So yeah, so with this I'm moving to my third example, which is on the third page, which is an interesting example, which is the inverse function f of x equals 1 by x, right? Now, this is the graph of the function, and when you look at the graph of the function, if you have understood the earlier examples of continuity, you will now know by looking at the graph that this function is discontinuous, and all that we're going to see is why is this function discontinuous, right? So let's pick up 2 points, right? Let's pick up f of 1, right? I'm going to copy this from the previous example, so you'll have to excuse me for that. Not required, right? Let's pick up f of 1. F of 1 is 1 by 1 is quite simple, so we have f of 1. Next, I have my limits, right? I'm going to go to my equation. I'm going to use limits. Now, x tends to 1 plus h, and this is my f of 1 plus h, right? Which is nothing but 1 divided by 1 plus h. 1 divided by 1 plus h, which is nothing but my 1 divided by 1, which is equals 1, right? So this is my right hand limit. Let me write this down here, and I'm going to go to the next line and do out my left hand limit. I'm going to copy this in the interest of time. So my left hand limit is 1 minus h, where x takes a value which is slightly lower than 1, and again I replace it in the function, and as h tends to 0, I get 1 divided by 1, which is nothing but my 1. So this function is continuous at x equals 1, right? So let me pull out the point on the graph. So this is where you have x equals 1, right? And so the function is continuous at x equals 1. Now, why is there a break in this particular graph as x tends to 0, right? Which means that there is something different which is happening at the point x equals 0. So the graph tends downward for all negative values near 0, and the graph tends upward for all positive values close to 0 but higher than 0, which is on your positive x-axis, right? So we're going to look at why is that. So people study the continuity of this function at x equals 0, right? So I'm going to rewrite this. What is f of 0, right? F of 0 is 1 by 0, which is infinite, right? Now I'll go to my right hand limit, and I'm going to replace it here with 0 plus h, which is 1 divided by 0 again, which means it is positive infinite, right? And one of the reasons I'm calling this positive infinite is, you will come to know that when I do the left hand limit at 0 minus h, right? So I'll go to my left hand limit 0 minus h, and I replace this and I get 0 minus h, which is 1 divided by minus h, which is my negative infinity, right? So for values which is smaller than 0, and which means it is negative, right? For a value which is very close to 0, this function takes negative infinity. And for a value which is very close to 0 but slightly greater than 0, this function takes positive infinity, right? So which means my LHL, which is my left hand limit, and my RHL, which is my right hand limit, are not equal. So one is tending to positive infinity, the other is tending to negative infinity, which is what you see in this graph here, right? So let me represent it here. This is my positive infinity and this is my negative infinity. So which means this function is continuous at the point 1, which we saw in the previous working, but it's not continuous at the point 0 because LHL not equals RHL at x equals 0 plus or 0 minus, right? Which means that the function is discontinuous at x equals 0. So in the subsequent videos, work out more complex examples. The reason I picked up these three are because they are simple and help you understand the basic concept of continuity of a function. So if we saw three functions today, f of x equals x square, which is your simple parabola, which we know that the function is continuous at all points, which means that this graph does not have a break at any point, right? It does not have a break at any point. It does not have a jump at any point. It is continuous in nature, right? Similarly, I come to f of x equals mod x, which is another interesting function. Here again, the function is continuous. It is continuous for all values x greater than or equal to 0, and it is continuous for all values x lesser than or lesser than 0, right? And we come here where we realize that the function is continuous at all points other than 0, and the reason is discontinuous at point 0 is because for values greater than 0, this function tends to positive infinity, and for values less than 0, this function tends to negative infinity, right? So I hope you have a basic understanding of what's a continuous function and why do we call a certain function continuous at a point x equals a, right? So that's all we have in this video today. Thank you for watching my video. Please do subscribe and have a good day. Thank you.